This video was made by the Bashar Suwele, explaining a lesson in analog electronic under supervision of Dr. Usama Cottonley.
Title: Ziner diode. Today I'm going to explain the Ziner diode, what it is, how it behaves in reverse bias, and why it's widely used for voltage regulation and shaping circuits. Ziner diode symbols and real packages. Here we see different Ziner diode symbols and common physical packages. The key idea is that a Ziner diode is designed to operate safely in reverse breakdown, so it can hold an almost constant voltage when biased correctly. Ziner 1 to 5 characteristic: current versus voltage. This graph shows the Ziner current versus Ziner voltage. In reverse bias, once the voltage reaches the breakdown value, Vz, the diode conducts and the voltage stays close to Vz while the current increases. Ziner diode voltage regulator plus Thevenin condition. This is a basic Ziner voltage regulator. Regulation happens when the Thevenin voltage seen by the Ziner is greater than Vz. The slide also shows the Thevenin relation using Vs, Rs, and RL. Currents in the regulator: Is, IL, Iz. Assuming the Ziner is conducting, the source current is Is equals Vs minus Vz over Rs. The load current is IL equals Vz divided by RL, and the Ziner current is the difference, Iz equals Is minus IL. This tells us how current splits between the load and the Ziner. Ziner wave shaping, clipping levels. This is a wave shaping or clipping circuit. The output gets limited at approximately plus Vz plus 0.7 volts on one side and around minus Vz plus 0.7 volts depending on the diode orientation. So Ziners are useful for protecting circuits from overvoltage peaks. In the second approximation, the Ziner diode is modeled as an ideal Ziner voltage source, Vz, in series with a small internal resistance, Rz. This makes the model more realistic because the Ziner voltage changes slightly with current. Deviation from ideal regulation, delta VL. Using that second approximation, the load voltage won't be perfectly constant. The deviation from the ideal value is delta VL equals Iz times Rz. So, as the Ziner current increases, the output voltage shifts a bit because of the internal resistance. Ripple reduction. Another benefit is ripple reduction. If RL and Rs are much larger than Rz, the output ripple is approximately scaled by Rz divided by Rs times the input ripple. So, a smaller Rz and a larger Rs generally improve ripple suppression.
Zener diode ratings. Zeners have important ratings. The maximum power is PZ max equals Vz times Iz max. They also come with tolerances like 20%, 10%, or 5%. The Zener resistance RZT increases near the knee of the curve, and there's usually temperature derating above about 50 degrees Celsius. Troubleshooting example: test node voltages. This slide shows a troubleshooting circuit and 3 cases of measured voltages at nodes A, B, and C. By comparing the node voltages, like VA equals 18 volts, and whether VB or VC are at 10 volts or 0 volts, we can infer if the Zener is regulating, open, or shorted. Load line idea: when Vs changes. Here we ask, what happens to Vz when Vs varies from 20 to 30 volts? The answer is found using load lines, graphically showing how the circuit equation intersects the diode characteristic for different supply voltages. Other diode types. Finally, not all diodes are the same. Examples include Schottky diodes for high-frequency switching, LEDs and laser diodes for light, step recovery diodes for fast snap-off behavior, back diodes that conduct better in reverse, and tunnel diodes with a negative resistance region. Other diode applications. And these diode types have real applications. Lasers in CD players and communications, step recovery diodes in frequency multipliers, back diodes as small signal rectifiers, and tunnel diodes in high-frequency oscillators.